Hello guys, welcome to a new video. On this opportunity I want to talk about the spherical pendulum, and we have this problem here. We have a pendulum consisting of a small mass that is attached to an inextensible cord and is rotating about one of the ends. The pendulum moves on a spherical surface, and we want to first obtain the equations of motion, and second discuss the conditions for which the motion of a spherical pendulum is converted into simple pendulum and conical pendulum. Okay, we have this figure right here. We have the Cartesian components. The relationship between the Cartesian components the spherical components are the following, are this one. So we have the x, y, and z components as the relationships between these components related with the polar spherical coordinates. So the z component, we have this z component right here. This z component is negative because we have our reference right here and the center of the coordinate components right here, and because we have a reference right here and the mass is below the reference, this component is negative, right? So the mass has those components, right? And we have the mass has a velocity v because the mass is moving, and the relationship between the square of the velocity and the square of the Cartesian components is this: x dot square plus y dot square plus z dot square, right? Okay, we know that the x, y, and z dot components are the derivatives with respect to time of those components, okay? And those are the components of the velocity on each coordinate, okay? Well, let's calculate those components of the velocity along the Cartesian components, right? So let's calculate x dot first. S dot first would be equal to the derivative with respect to time of x, right? And that would be equal to the derivative with respect to time of, okay, we know x is L sine of theta, sine of phi. Okay, we can use the product rule. Do you remember the product rule, right? We do this. This is equal to L, right? And we take the derivative. Okay, L is constant, okay, and we take the derivative of the first term with respect to time. That will be theta dot cosine of theta cosine of phi, okay. Sorry, here is cosine of phi, plus this is the derivative of the sine of theta with respect to time, okay? This first term multiplying the second term plus the first term sine of theta multiplying the derivative with respect to time of cosine of phi, but the derivative of cosine of phi is minus sine of phi, right? We have to do this, taking the derivative with respect to time of the argument, and after we take the derivative of the function, and this is minus sine of phi. Okay. Okay. I will reorganize this expression and I will rewrite it, and we will have the following equation. This is what I got when I rewrite this derivative, and I reorganize. What I did is I multiply L by every term into the parentheses. Okay, this is a bracket. I reorganized these expressions, and what I got is this. Okay, and okay, we need to take the, because we want to take the square of this expression, and this would be, okay, that would be the square of this expression. Okay, we want to use the formula, the perfect square formula, and this perfect square formula says that a plus minus b squared is equal to the square of the first plus the square of the second term plus minus 2 the first multiplying the second term. You know that expression already. I just wanted to remind it, but you know that it's pretty easy. And we apply this formula into the last expression that we got. We will have, for example, we will have x dot square equal to, okay, the first term square would be this term square, okay, and that would be L square theta dot square cosine square of theta cosine square of phi, okay, plus the second term square, okay, plus L square phi dot square sine square of theta sine square of phi, okay, plus, okay, in this case is minus 2 times the first term multiplying the second term, okay, minus 2 times the first term multiplying the second term, that would be L multiplying L square multiplying L square would be L4 theta dot square phi dot square cosine square of theta cosine square of phi sine square of theta sine square of phi, okay, that's what we got, sine square of phi. That's what we got. I will highlight this equation. Let's call that equation number 2. Okay, something that I forgot to write down is to call this equation number 1. Okay, guys, equation number 1, and we have here equation number 2. We do the same for the y component, okay, the y component. We know that the y component is, for the y component we know that y dot is equal to the derivatives with respect to time, and the y component is L sine of theta sine of phi, okay. Okay, the derivative with respect to time, L is the length of the chord, is constant. We can take it out of the derivative. We have, this is the derivative with respect to time of this product. Okay, we take the derivative of the first term would be the derivative of the argument multiplying the derivative of the function, multiplying the second term plus the derivative, okay, plus the first term sine of theta multiplying the derivatives of the second term. The second term would be the argument, the derivative of the argument multiplying the derivatives of the function. Okay, I will reorganize and rewrite this term as I did with the S component, and that's what I got, reorganizing and rewriting this derivative. Okay, now we want to calculate the square of this expression, right? Y dot square, and y dot square would be this expression. Okay, we do the same process as we did with the x dot square, using the perfect square formula on this expression, and doing the same as we did with x dot square. When we do that, we get the following expression. Well, and this is equation number 3. Now for the z component, we know the z component is equal to minus L cosine of theta, then z dot would be the derivative with respect to the time of this, and that would be minus L multiplying the derivative with respect to the time of cosine of theta, that would be theta dot, multiplying, theta dot is the derivative of the argument, multiplying the derivative of the function. The derivative of cosine is minus sine of theta. Then z dot would be L theta dot sine of theta. Okay, z dot square would be equal to L square theta dot square sine square of theta. Okay, let's call that equation number 4. Now what we have to do is we need to do the following. We know that v squared is equal to x dot square plus y dot square plus z dot square, and we need to add up equation 2, 3 and 4, okay, to get the velocity, right? To get the velocity square of the mass. Well, we need to do that. We know that we have here equation number 2, okay, we have equation number 3, and we have equation number 4. Because especially equation 2 and 3, they are long, I will write the equations, the summation. I will write it down, and we will get the following. Okay, this is what we got when we adding up equations number 2, 3 and 4, right? These terms that I am highlighting with yellow, they are subtracting each other because they are equal, and finally we get the following equation. Okay, this is what we got, right? Now we have these terms right here. For example, we have the terms that are highlighted with green. Okay, let's see those terms highlighted with green, and let's see those terms highlighted with blue. Okay, as you can see, these terms, they have, for example, the terms highlighted with green, they have the common factor L squared phi dot square. Okay, I made a little mistake. Let's do something here. Is the terms highlighted with green, L theta dot square, and this, okay, this one is theta dot square. Sorry, I made a little mistake. This is theta dot square, sorry. This is theta dot square, okay? Okay, now we're good. This is, these two terms that they are highlighted with green, they have the common factor L squared theta dot square and L squared theta dot square, okay? Plus cosine square. Okay, sorry guys, I made a little mistake. I need to, okay, here I have to have cosine square of theta. Sorry, because I wrote a lot of equations and I made a little mistake too, but now I'm good. Yeah, now we are good. Now we have these two terms that are highlighted with green and these two terms that are highlighted with blue. Okay. Okay, as you can see, this is common factor, this L squared theta dot square cosine square of theta, and L dot square theta dot square cosine square of theta. They are common factor on those two terms, okay? With the terms that are highlighted with blue, we have L square phi dot square sine square of theta. L square phi dot square sine square of theta. Okay. Okay. With those terms, taking common factor from those terms, we have the following equation. We have v squared is equal to L squared theta dot square cosine squared of theta cosine squared of phi plus sine squared of phi plus L squared phi dot square sine squared of theta multiplying sine squared of phi plus cosine squared of phi. And we have obviously the last term of the equation, L squared phi dot theta dot square sine squared of theta. Okay, we know guys that this is equal to 1 because the trigonometric identity sine squared plus cosine squared is equal to 1, and we have then that the velocity is equal to L squared theta dot square, this term plus this term cosine squared of theta plus L squared theta dot square sine squared of theta plus this term that will be equal to L squared phi dot square sine square of theta. Okay, L squared theta dot square and L squared theta dot square are common factor. It's a common factor, so we have L squared theta dot square multiplying cosine squared of theta plus sine squared of theta plus L squared phi dot square sine square of theta. Okay, this is equal to 1, we know. Then the velocity is equal to L squared theta dot square plus L squared phi dot square sine square of theta. We know guys this is a little bit exhausting and long, but we needed to calculate this velocity in polar spherical coordinates. Okay, then we can write the kinetic energy. Okay guys, let's call this equation number, before writing the kinetic energy, we can call this equation number 5. Let's call this equation number 5. And we can write the kinetic and the potential energies, both energies. So we can write K, that is kinetic, and phi, that is the potential energies. Okay, so we know that the kinetic is one half of the mass multiplying the velocity square, and then we have K equal to, we can call it K or T, right? We can call the kinetic energy K or T. Okay, then this is equal to 1/2 of the mass velocity square. That would be 1/2 of the mass. Oh, we know the velocity square already. Okay, equation number 5. L square, I took common factor out, L square, and I get theta dot square multiplying phi dot square sine square of theta. And the potential, you know that the potential energy is mass multiplying the gravity multiplying the z position. Okay, and then v is equal to minus mgl cosine of theta, because the z position is minus l cosine of theta. Okay guys, then by definition the Lagrangian is equal to kinetic minus potential. Okay, I know I wrote kinetic like K, let's write it like T in order not to get lost with the notation, so to have a consistency with the notation. Okay, that's the Lagrangian, the definition of the Lagrangian. Okay, okay, then the Lagrangian would be the kinetic 1/2 of the mass L square theta dot square plus phi dot square sine square of theta minus the potential energy. Well, the potential energy is minus mgl cosine of theta, then we have plus mgl cosine of theta. Let's call this equation number 6. This is the Lagrangian of the system. Okay, we already know the Lagrangian of the system. Okay guys, what we can do now is calculate. Okay, we need to calculate the equations of the Lagrange equation. Okay, and we know that the Lagrange equation is derivative with respect to the time of the dl. Let's do it for the variable theta, dl d theta dot minus dl d theta, and that's equal to 0. Okay, that's the Lagrange equation. So for theta we have dl d theta dot is equal to, okay, the derivative with respect theta dot of the Lagrangian would be 1/2 of the mass L square. Okay, what is the derivative with respect theta dot? Is 2 theta dot. Everything else is 0 because the other terms, they don't depend on theta dot. We cancel these 2 with this. This would be okay, this will be m L squared theta dot. And now we calculate the derivative with respect to the time of this expression. That would be the derivative with respect to the time of dl the theta dot. That would be m L squared theta 2 dots. Okay, and the derivative with respect theta dot would be 1/2 of the mass L squared. That would be the derivative with theta, with respect theta of this expression, because of this expression. Okay, those two terms are the terms that depend on theta, and we take the derivative with respect theta of those two terms, and that would be 2 sine of theta cosine of theta phi dot square, okay, minus mgl. Okay, the derivative of cosine of theta is minus sine. I have the minus sign here already, and this is sine of theta. Okay, so the Lagrange equation we know is, we get this term and this, and we replace those two into the Lagrange equation for theta, and we get m L squared theta 2 dots minus m L squared sine of theta cosine of theta phi dot square minus plus mgl sine of theta equals 0. Okay, dividing the equation, okay, the mass cancel because it's common on each factor, on each term, sorry, and we can divide all the equation by L square and L square. Doing that, we get theta 2 dots minus sine of theta cosine of theta phi dot square plus g dividing L sine of theta equal to 0. Let's call this equation number 7. Okay, and now do the same for the variable phi. Okay, let's do the same for the variable phi. dl the phi dot is equal to 1/2 m L squared. Okay, that will be 2 phi dot sine squared of theta. Okay, the derivative with respect phi dot of this, that will be 2 phi dot sine square of theta. 2 cancels with these 2, they cancel each other, and we have m L squared sine squared of theta phi dot. Okay, then the derivative with respect to time of dl the phi dot is equal to m L squared sine squared of theta phi 2 dots. Okay, let's write it like this better, because I want to do something. Let's write it like derivative with respect to time of m L squared sine squared of theta phi dot. Okay, and that will be equal to 0. Okay, and now let's do the derivative with dl the phi. Okay, let's go to the Lagrangian. The Lagrangian doesn't depend on phi at all. Okay, we don't have any dependence on phi, so you see this equation and we won't see any dependence on phi. then the derivative with respect to phi of L is equal to 0. Okay, so the Lagrange equation will be only this equation, only this part. Okay, and we can call this equation number 8. We can call that equation number 8, the equation that is highlighted. Okay, what we can do now is, because equation 8 is derivative with respect to time. Okay, let's write this equation real fast. What I'm gonna do is to take out the what I'm gonna do is to write this equation number 8 like this: m L squared derivative with respect to time of sine square of theta phi dot equal to 0. Okay, because this derivative is equal to 0, that means that this part is a constant. Okay, this part is a constant because the derivative with respect to time is 0. Then we have that sine square of theta phi dot is equal to a constant c. Okay, basically that's what we got. And let's do something. Let's take this from the last equation. Let's clear the phi dot term. So from this last equation, actually we can call this equation number 9. From equation number 9 we have phi dot equal to c dividing sine square of theta. Okay, replace 9 into equation number 7. When we do that, we get theta 2 dots minus sine of theta, okay, cosine of theta phi dot square. Okay, but phi dot is z dividing sine square, right? So but we have phi dot squared. Okay, we have on equation number 7 phi dot square, and we need to put this square into here, so we have c squared dividing sine 4 of theta plus g dividing L sine of theta equals 0. We simplify this part with this. Finally, I will rewrite this equation like this: theta 2 dots plus g dividing L sine of theta minus c squared dividing sine theta cube equal to 0. Let's call this equation number 10. Okay, we have to consider something here. This equation number 10 is an equation that is only depending of theta. Okay, why we got this equation like this is because, okay, we got the equation of motion for the particle on equations number 7 and equation number 8. Okay, but you remember that we want to take some considerations. Okay, this is the spherical pendulum, but we want to see under which conditions this spherical pendulum behaves, first as a simple pendulum and second as a conical pendulum, right? Now we will do that starting from equation number 10. Okay, but we also we can call equation number 8, we can call this equation dl d phi dot. We can call from equation number 10, actually it's from this part, we can call dl, actually I will write it on the next page, dl d phi dot, we can call that equation p phi. Okay, and we know that p phi is equal to m L squared sine square of theta phi dot. Okay, but we come back to this part of the problem, and we know that when we take the derivative of respect to time with respect to time of that expression, that is equal to 0. Okay, that means that this is a constant of motion, this part p phi, we are calling this part p phi, and this is a constant of motion. Okay, and it is recognized as the angular momentum of the system about the z-axis. Okay, it's the angular momentum of the system about the z-axis. It is conserved. Why this part is a constant and why it is conserved? Okay, it is conserved because the torque is not produced either by the gravity or the tension of the core about the z-axis. Thus, the conservation of angular momentum is reflected on this expression. Okay. Now we want to talk about the two cases that the problem is asking for. First, we have two cases, but we want to talk obviously about the first case first. First, suppose that phi is constant. Okay, if phi is a constant, then phi dot is 0. Okay, because phi dot is the derivative with respect to the time of phi and is constant. Okay, if phi dot is 0, if we come back here, if phi dot is 0, and we see equation number 9, from equation 9, if phi dot is 0, then z is 0. Okay, because sine square, okay, because you can, if phi dot is 0, then sine square of theta cannot be 0. Then z is 0. Okay, then z is 0. And the equation number 10 reduces to theta 2 dots plus g dividing L sine of theta equals 0. This equation is appropriate for a simple pendulum in which the bob oscillates in the vertical plane. So you know already this equation. This is the equation of a simple pendulum. Okay, and that's the first case that we are considering right here. Now let's consider the second situation. Okay, the second situation is, suppose that phi is constant. Suppose that theta is constant. Okay, then from equation 9 again, we go to equation 9 again. If theta is constant, then phi dot is constant. Okay, why? Because theta is constant, then phi dot is constant, because c is a constant. Okay, this term is a constant and this is a constant, then this term is a constant. Okay, and from equation number 10, okay, let's put theta 2 dots equals 0. Okay. Then from equation number 7, let's say equation number 7. Okay. From equation number 7 we have theta 2 dots minus sine of theta cosine of theta phi dot square plus g dividing L sine of theta equal to 0. Okay, let's say that theta 2 dots is 0. Then we have this 0. Yeah, theta 2 dots is 0 because theta is a constant. Okay, then the derivative with respect to time and the second derivative with respect to time are 0. Having this, we can write this equation like this: g dividing L sine of theta is equal to sine of theta cosine of theta phi dot squared. Okay, sine of theta cancel with sine of theta. Then cancelling sine of theta, we have that phi dot square is equal to g dividing L cosine of theta. Okay, let's call phi dot equal to omega. Okay, if we call phi dot equal to omega, then we have that phi dot is equal to omega, and that is equal to the root square of g dividing L cosine of theta, or g dividing h with h equal to L cosine of theta. And we have a period. This is a frequency, okay? Let me write it better here. L H L cosine of theta. Okay? This is the frequency of the pendulum. And the period t equal to 2p dividing omega, that's equal to h dividing g. Yeah, that's the period of the pendulum. Okay, guys, what does this mean? This is appropriate for the conical pendulum, in which the bob rotates on horizontal plane with uniform angular velocity, with the core inclined at a constant angle theta with the vertical axis. Okay, guys, this is a problem. I know it was a little bit long, a little bit exhausting. Hopefully you like it. You can give me a thumb up, subscribe to my channel, give me a like if you like it, and see you in the next video. See you next time. Bye.